Thank you, Mr. Chairman, for the kind introduction. Good afternoon, ladies and gentlemen. Today I will be talking about the development of hollow-core photonic bandgap fibers, and in particular their application for gas sensing at mid-infrared wavelengths. This work was carried out at the Optoelectronics Research Center and at the EPSRC Center for Innovative Manufacturing in Photonics at the University of Southampton, UK. So this is the outline of my talk today. I will begin by giving the motivation for the work, and I will also briefly summarize the recent developments that have happened in the field of hollow-core photonic bandgap fibers, mainly driven from other application areas. I will then show that the operation wavelength of these fibers can be extended to mid-infrared wavelengths. I will then discuss fabrication and characterization of mid-infrared operating hollow-core bandgap fibers made of silica glass. And in doing so, I will also briefly describe the characterization tools that we have developed for this purpose. And finally, I will present gas sensing results, focusing on acetylene and ethane, and show our efforts towards achieving sub-ppm sensitivity. So, as you all well know, there are many well-established optical methods for detection of gases. On the other hand, optical fibers have, as a sensing platform, hold some very key advantages. And people have been looking at conventional fibers and try to apply these advantages to chemical sensing and gas sensing. So the main advantages of a fiber platform is really the compactness, small size, lightweight, robustness, the low cost, the high thermal and chemical durability of the silica glass, which composes the fibers, the widespread availability of fiber components, sources, detectors, couplers, gratings, and the possibility for highly efficient and sensitive sensing schemes, including distributed sensing, remote interrogation, highly sensitive interferometric schemes. On the other hand, when one is looking at chemical sensing application and gas sensing application, there are some important limitations. And these are the two that I would like to highlight today. First off, it's very difficult to create an efficient interaction between the analyte, which is the gas outside the fiber, and the light, which is guided within the fiber. So people have been looking at ways of accessing the evanescent field within the fiber by thinning the cladding, tapering fibers, or perhaps creating free paths within the fiber by etching the fiber itself or putting back reflectors at the end of fiber. All these approaches provide relatively small improvements in the sensitivity, and they also might affect some of the advantages I mentioned before, mainly the compactness. The second limitation is that really conventional fibers operate well all the way to 2 micron wavelengths, and thus they can only target the so-called near-infrared overtone bands, which are quite weaker than the fundamental overtones that lie in the mid-infrared. So one would really like to access mid-infrared bands, the strongest bands, but this is impossible using conventional all-solid silica fibers. One would have to use chalcogenides or fluorides, and these kind of fibers don't have the good properties that I mentioned before about silica fibers. On the other hand, the advent of hollow-core microstructure optical fibers now provides a clear strategy to overcome the limitation of conventional solid fibers. And this is the fiber I'm talking about. It is mainly composed of a periodic lattice of hair holes and glass rods, which composes the cladding of the fiber. This periodic lattice creates an optical bandgap in the direction of propagation of light. Then a hollow core is formed by removing a certain number of elements at the center of the photonic crystal cladding, typically 7 or 19 elements. And in this way, low-loss optical modes, air-guided modes, can be guided within the core at wavelengths within the optical bandgap, and one would normally see this typical transmission spectrum here characterized by a central wavelength and a limited bandwidth. Now, because the light is traveling in a hollow core with minimal overlap with the silica structure, there's a number of interesting and very enabling properties. First of all, optical nonlinearity and bulk loss mechanisms are much reduced, typically by a factor of by 3 orders of magnitude. And we now have potential for very efficient light-matter interaction, typically with gas, if we have the gas inside our hollow core. Plus, because the bulk loss mechanisms are now much reduced, we can think of extending the operation wavelength of this fiber to longer wavelengths. Now, hollow core photonic bandgap fiber have been around for a number of years, but their development has accelerated in recent years, and this has been driven by interest in transmission fibers, so in telecom research. Now, the interest in these particular fibers lies in their ultra-low nonlinearity, the potential for ultra-low loss, and a number of other interesting properties for telecom applications. The point I would like to make is that very substantial fiber improvements have been achieved over the past few years across the board. And this includes fabrication technologies. Now we can fabricate this fiber in multi-kilometer lengths with very high structural consistency. We have progressed in the understanding and control of the optical properties of these fibers, which are rather complex. So, for instance, we are now able to suppress these unwanted surface mode resonances, and we can obtain low-loss fibers with very wide transmission bandwidth. Now, these fibers meet very strict requirements for coherent data transmission at very high rates, approaching 100 terabit per second. And the availability of such improvement fibers is now set to benefit other application areas, and in particular, the areas in sensing. So if we look at the loss versus wavelength behavior in these fibers, one can see that the two main loss mechanisms are a surface scattering mechanism, here characterized by lambda to the -3 dependence, and the material absorption, which is typically reduced by 3 orders of magnitude. This has 2 implications. First off, the minimum loss is normally found around 2 microns in this fiber, rather than the more usual 1.5 in conventional fibers. The second is that looking at longer wavelengths, it should well be possible to obtain losses well below 1 dB per meter at wavelengths around 3 microns and beyond. So this is how these fibers are fabricated. First step is to prepare the stack of capillaries. These are drawn a first time to produce what we call a cane, which is millimeter size. This is then placed in another jacketing tube and drawn to the final fiber size. And these are the structural properties of the fabricated fiber operating in the mid-infrared. It is what we call a 19-cell core structure. The average cladding pitch, which is the hole-to-hole spacing here, and the core diameter is upscaled as compared to fibers operating in the infrared in order to achieve the correct operation at long wavelengths. These fibers are expected to be few moded, but they can be operated as virtual single modes, and we can fabricate lengths of the order of 100 meters or a few hundred meters and limited by the preform size. So before I present the results of the characterization, I would like to introduce a tool which has allowed us to do this measurement. This is a special supercontinuum source which is based on a fluoride fiber and on a pumping scheme at 2 micron. So this is the diagram of the pump source. This is based on a gain switch laser diode operating at 2 micron, which undergoes 3 steps of amplification through 3 thulium-doped fiber amplifiers, the last a high-power amplifier, to provide an output of the order of 30 picosecond and 100 kilowatts, very high power. So this is then passed on to a commercial fluoride fiber to create a very broad output and a supercontinuum approaching the power of actually over a power of 1 watt. And these are the spectral characteristics of this source. As you can see, we have a very broad output ranging from the edge of the visible side of the spectrum all the way to 4 micron. Plus, it's a very flat spectrum, particularly in the long wavelength side, which is the most interesting for this work. And also, the output has very good temporal stability, with variation less than half a dB in the order of a half an hour. So this 2 micron pumped supercontinuum source provides an ideal source for broadband mid-infrared spectroscopic measurements with high signal-to-noise ratio and uniform spectral sensitivity. This is the characterization of our fiber. Here you see the transmission over a short length of 5 meters and the loss measured by a cutback measurement. As you can see, there is a rather complex loss structure. This is actually due to small amounts of hydrogen chloride which result from the fiber fabrication. So as soon as it is fabricated, the fiber is already working as a gas sensor. This hydrogen chloride can be removed simply by flushing the fiber. And if you do so, you will find a loss of less than 1 dB per meter over a very wide range of half a micron, a minimum loss of 0.05 dB per meter, transmission all the way to 3.8 micron. I would like to remind that this is a silica fiber, and this is compares with losses of the order of several hundred dB per meter of the bulk silica glass. Also, more interesting for a sensing application, this fiber can be bent at basically no loss penalty. So now, by putting together the two technologies, this supercontinuum source, very bright, very powerful, with very broad output, and the fiber, you can see that we have a very important and interesting tool to analyze a number of gas formulations. And here we have applied this concept to the detection of acetylene at 3.05 micron. So acetylene have been studied very thoroughly at near-infrared wavelength, but here we are targeting the fundamental band. And we are using a 1.4 meter long fiber filled with 2.5 volume percent. And we achieved 25 dBs dynamic range at a very high resolution of 0.2 nanometer using the latest generation OSA, long wavelength OSA from Yokogawa. So as you can see, we have excellent agreement with iTrend data, and the strongest line are saturated, which is testifies the fact that these bands are now much stronger than the near-infrared counterparts. So we then moved to ethane, and here we consider a much more dilute solution of about 50 ppm ethane in nitrogen. So ethane has relevance for industrial, environmental, and medical application, and has a strong absorption around about 3.35 micron. And as you can see, here we are using actually a longer, slightly longer fiber sample. The dynamic range is comparable due to the low fiber loss, and we have excellent agreement with theory. And from a noise floor about 0.1 of dB, we can estimate the limit of detection below 1 ppm. And I should also point out that there is potential to substantially improve this sensitivity by increasing the fiber length or reducing the modal noise and using more sophisticated detection techniques. So I'm now to reach the summary and conclusion of my talk. So hollow core bandgap fibers offer an ideal platform for highly efficient light matter interaction, in particular for gas sensing. I hope I've convinced you that there have been very substantial recent developments, which, although they have been driven by telecom research, are set to benefit adjacent application areas, and in particular sensing. We now have hollow core fibers that operate with sub-dB per meter loss all the way to 3.6 microns, and we believe there is substantial scope to further extend this range to longer wavelengths. These fibers enable targeting the strong fundamental absorption bands, and in this work we have presented analysis of acetylene and ethane gas. And through simple single-pass broadband transmission measurement, we have demonstrated sub-ppm detection sensitivity. Further improvements appear entirely feasible by using more sophisticated sensing scheme, as mentioned before. Thank you.